Now, talking of variance reduction techniques, now we saw the point of n, so I've just repeated here for convenience. Now, another alternative way in which we can keep a check or we can control the amount of sampling error which is there in the Monte Carlo are a couple of variance reduction techniques. Now, we'll talk of two popular techniques which you commonly observe. One is what we call as antithetic variates, and next is control variates. So we'll run through both of them and you'll have clarity on this further. Looking at antithetic variates. Now, here the idea is we are trying to reduce the standard error or the sampling error of a Monte Carlo simulation by rerunning the simulation using a complement original set of random variables. Because remember that in the Monte Carlo simulator, we'll have that phi, which I have written on the whiteboard, which is the random number draw, right? So in the antithetic variate case, we'll have to use a complement of this, which we use as a part of the simulation exercise. So imagine that the original set of random variates is given as xt. If we rerun the simulation with the complement set, then we are going to stick to the complement of this random variable xt, which we then call as minus xt. Now, again, these two sets are perfectly negatively correlated. So if we take correlation between xt and minus xt, which are complements of each other, that will naturally be -1. Now, we try to understand how exactly the antivariate technique comes to our rescue in reducing the quantum of standard error which goes into our simulation work. So to understand this, what we do is we look at an example whereby we don't use the antivariate technique first. We'll use the usual plain simulations, and then we'll see what is the benefit of having an antivariate or antithetic variate example so that it brings down the overall sampling error. So let's see how it works. So we'll consider a simulation of two sets of random numbers. It could be anything. So let's not worry about what the underlying asset or what is the underlying quantity, etc. Let's take just two random set of numbers, and we initially start without using antivariate techniques. So we do plain and simple simulation, just what we have discussed so far. So we stick to that for first. Next, we calculate the average output value of the above, and I would like to call that value as x bar, and x bar is x1 plus x2, where x1 and x2 are the average output parameter values for two simulation sets. Now, if we have to calculate the variance of this average value, it can be represented in this way. So we are having the variance of x bar on the left hand side, and on the right hand side we have the calculation. Now, if we don't use the antithetic variates case, then in that case, the two Monte Carlo replications which are done, they are completely independent of each other. And because they're independent of each other, the last covariance term is going to vanish. So all that we are left with is variance of x bar is the thing on the right hand side. Now, if we look at the antithetic variate case, now up till now, we have stick to the simple thing without antithetic variates. Now imagine that we are using antithetic variates. Then we can focus on step number 3. So here the main thing that changes is this covariance term won't vanish. It will remain, but this will be negative because we know that we are just using a complement of the same random variable. So that way so this will be a negative quantity, and since this last term is negative, naturally it is going to bring down the overall variance. And it is because of this reason, rather than using two random sets, the usual simulation, if we decide to use an antithetic variate case, then in that case, we'll have a lower overall variance of the final output. And that is how it can help us improve our accuracy, i.e., it can bring down the sampling error which is there as a part of the simulation model. The next way to do that is a control variate. So we saw antithetic variate. Now let's understand what is a control variate technique. Now, under this technique, what we attempt to do is we replace a certain variable x under simulation, and this has unknown properties, and we try to use something which is similar to x. So imagine that we have some similar variable y, but it has its known properties. So we have two things in play here. So we have a certain variable x whereby we don't know what are its properties, and that's what we are trying to handle. And to make our life easy, we try to look at another variable y whose properties we know beforehand. And that is something which is going to make our computation easy. So to understand how this approach works, so we'll do two separate simulations, one on variable x with unknown properties, and next is on control variable y with known properties. And we use the same set of random numbers. Now, assume that Monte Carlo simulation estimates of variables x and y is denoted by x kappa and y kappa. Now, the original estimate of x, let's call it as x star, because if we write it that way, it will be easy for us to then bifurcate between this. So I'll just prefer to call it as x star, and x star will be given by this formula. Now, this new variable x star will have a smaller sampling error than our original variable x, which we had started off with, if the control statistic and the statistic of interest, they have a high correlation. If that happens, then the overall sampling error is going to come down. So as the sampling error comes down, we know that the accuracy of the simulation improves.